So here is our, what we call Dallas discharge assisted laser ablation source. You can see where the general valve pulse nozzle is, and then the rotating rod. The laser comes in here, and then we shoot everything out through a discharge nozzle. And for example, in the case of scandium, we apply about an 800 volt discharge. And that's what enters our chamber. Without the discharge, we don't make these molecules. Okay? And this was a graduate student of mine named Sun that came up with this idea. So we were able to measure in our Fourier transform microwave spectrometer the pure rotational spectrum of YC2, and of course the next metal above the entry of the scandium. And so we felt, well, the chemistry should be similar, and we'll just try this sort of source and see if we can find it. And we were lucky because we didn't have to scan too much. The theory was actually fairly good for the rotational constants. And here's the spectrum of the 1 to 0 transition. And you can see here, in addition to being an asymmetric top, so you have Ka and Kc quantum numbers, you have spin rotation splitting due to the unpaired electron, and then you have some of the many various scandium hyperfine components. And these are, the Doppler components of the classic Fourier transform spectrum. That's at 16 gigahertz. Then we went on to measure the 2 to 1 transition at 31 gigahertz. There's most of the hyperfine components we measured. And then, thank God, we could move up because even with 1 to 2, 1 to 0, and 2 to 1, we didn't have enough data to model to fit it with the proper Hamiltonian, so we were able to measure the 3 to 2 at 47 gigahertz, any of the hyperfine components. And then finally, 4 to 3 to 62 gigahertz. And then we decided to do an isotopic substitution so we could get a better structure. And if you doubly substitute carbon-13, you don't get any carbon-13 hyperfine structure because spin adds for I equals 0, and that's the only way you can measure, get the K equals 0 line, so we don't have any carbon-13. But if a singly substituted scandium dicarbide does have carbon-13 hyperfine structures. You've got the scandium and then the carbon-13 on top of that. So it gets to be a little bit complex. And we're still trying to measure more lines of these two because we don't quite have the hyperfine structure. However, with the main isotope and with what we had, we could determine the structure and fit the data with a classic asymmetric top Hamiltonian that includes spin rotation, magnetic hyperfine, quadrupole, and here are various constants for scandium dicarbide. We couldn't, of course, independently determine the rotational constants needed for asymmetric top. We have the ratio fixed in theory. And you can see we determined the magnetic hyperfine and one of the quadrupole components. And one can actually compare the quadrupole components, the quadrupole constant to that for these diatomic molecules and perhaps say something about bonding. So here's scandium sulfide, really ionic ones are scandium fluoride and scandium chloride, that's 74 and 68 megahertz. For scandium dicarbide, it was more like 49 megahertz. More similar to what we see for scandium sulfide. And so we believe that that means that there's somewhat more covalent character in scandium dicarbide than native ones. It's very qualitative. One of the more important things we did was to determine the structure of scandium dicarbide with carbon-13 substitutions. There it is. Scandium carbon bond length of 2.057, carbon-carbon bond length of 1.26 angstroms. And that was pretty much in agreement with theory, but for comparison, here's the endofullerene structure with 2 scandium atoms in the two carbons. The scandium carbide bond length in that case is about 2.26 angstroms, which is longer, and the carbon-carbon bond length is 1.4 angstroms, which again is somewhat longer. So having obviously 2 scandium atoms on either side sort of pulls the molecule apart. But of course, scandium does not have a high cosmic abundance, although I've been thinking about it, I really need to go check some spectra. And of course, we'd like to try these dicarbides with more abundant metal. And aluminum was just something we decided to try. It's not a 3D metal, but it was certainly interesting because there had been laser-induced fluorescence work by various other groups, so we had some estimates of the rotational constant. And one once again, we were able to make this with this discharge source coupled with the laser ablation. And so far, we've been able to measure the 1 to 0, several hyperfine components. One of them has a square of 5 halves, the 1 to 0 transition, the 2 to 1, and some lines of the 3 to 2. But it's not very easy to make, and we really need more lines in order to get a good spectroscopic fit that's unique. And so we're going to have to try to measure more lines and improve our signal to noise. The 3 to 2 is up at 65 gigahertz. And the next transition up is very difficult to do, so this is work in progress. Some nice spectra, we need more lines. It's an asymmetric top, it's hyperfine. We've got to get more data for a better fit. So that's work in progress, and we don't really have enough spectroscopy done to really confidently search for this molecule in interstellar space. And so, like I said, more work needs to be done. Now, another species of interest in these 3D monodicarbides is titanium carbide. And we actually started looking for that the minute we found scandium, and we couldn't find it in the Fourier transform machine, so obviously things are getting more difficult. And so we decided, well, we need more experience with titanium. We hadn't done too many titanium molecules. And so I had a very good undergraduate this summer working for me, and I thought, well, you know, we need more experience with titanium. Why not do the isotopologues of TiO? It's an oxide, and metal oxides are fairly easy to create. At least that's been our experience. It has an interesting ground state, triplet delta regular, and there are 5 isotopes, and only the main isotope has been studied in titanium oxide. That's titanium 48, which is about 34% abundance. Then you get titanium 46, 47, 49, and 50, and 47 and 49 both have nuclear spins of 5 halves and 7 halves. So now you get some nice hyperfine structure to study, and it seemed like a good project for this right undergraduate. And another thing is that astrophysically, titanium isotope anomalies have been found in grains they extract from meteorites that supposedly come from stars. People are interested enough in these various ratios that they actually try to measure the titanium isotope ratios by looking at optical lines of TiO in stellar spectra. Of course, they didn't have the resolution. So there is a astrophysical motivation to look at these isotopes as well. As I said, 2 of them have nuclear spins. And so that was the deal, was to work with titanium, and as a high melting point, this was the work of an undergraduate who also was in the police force. He actually put the police force to do spectroscopy. And he worked all summer or part of the summer, and got a really good way to melt titanium in a broiler oven and produce a lot of it, which was really kind of interesting. And so he was going to start this out in the Fourier transform machine and laser ablate titanium, and it was a broken part. We were waiting, so I said, just play with the broiler ovens. And he got them to work really well. And so by vaporizing titanium and adding either N2O or O2, he was able to obtain these really beautiful spectra of titanium oxide in its triple delta state. Here's the energy level diagram. So you have 3 omega ladders. In addition, for the 49 and the 47 isotopes, you have nuclear spins, so you get hyperfine. So here we see spectra of 1 rotational transition, 13 to 14. In the 3 omega ladders, here's the 47 isotope, spin of 5 halves, a nice sextet. Omega equals 2, omega equals 3, that's an interloper. Same thing for 49 titanium. And he measured about 10 transitions for those 4 isotopes. And then he did some additional Fourier transfer microwave work to get a few more transitions of lower frequencies. So this is just a small section of all the frequencies he measured for this project. 2 to 1, 7 to 6, 8 to 7 of the 49 isotope, and he did all 4 isotopes. 2 of them, like I said, have nuclear spin, measured 10 transitions of each between 62 and 420 gigahertz. Measured lines in all 3 spin orbit ladders, hyperfine components, over 400 individual lines. It's a fantastic job. Too bad he's doing astrobiology now. But anyway, so this is our fit for the data, and I had to show this purposely for Bob. So, you know, triplet delta, we're fitting rotational constants. This is spin orbit's fixed. We fit the centrifugal distortion, spin orbit, spin, spin. And then the titanium hyperfine. And you notice this funny constant delta A. A here is the nuclear spin orbit hyperfine constant. B is sort of the Fermi contact term, and C is the dipolar term, and then we have quadrupole terms. We had to put this delta A term in to the Hamiltonian. We had to do this before for the omega equals 2 data, because we couldn't fit it otherwise. And so we just incorporate this sort of fudge factor so we can fit the omega equals 2 data in along with the 1 and 3. And of course, this arises because the omega equals 2 substate is obviously perturbed, most likely by nearby singlet delta state. And of course, we could do some more modeling with this, but we're sort of writing up the paper right now. So this was the work of Andrew Lewinsky, a summer project. Anyway, so that's kind of very classical spectroscopy that we've done pretty recently. We hope to be able to now go on and do titanium dicarbide in the lab and measure that spectrum and continue on along the 3D metals to look at these interesting species. But now I'm going to switch gears a little and talk about detecting a new interstellar molecule on the basis of rotational spectroscopy. And the big question here is, we've talked about C60 and C60 plus in the rotational spectroscopy, the biggest molecules like HC11N. And so one wonders, what is the extent of chemical complexity out in interstellar space? And this is kind of important because some of this material is going to end up on planet surfaces, and so, it'd be good to know how complex molecules can get and how they might influence chemistry on a planet's surface. But complex molecules have complicated spectra because they're asymmetric tops, they're not diatomics like we were looking at, and radio telescopes can't differentiate between different sorts of mixtures. You get what you get, right? And if it's a big, complicated mixture, you have to unravel it. So you have this big problem of line confusion in interstellar spectra that you don't have in the laboratory, so it makes things very tricky, and there's been a lot of misassignments, or some misassignments. And our solution to this sort of complex problem is we ended up doing a broad spectral-wide survey of one very famous cloud in the galactic center called Sagittarius B2 North. And we measured its spectrum continuously from 68 to 116, 130 to 172, and 210 to 280 gigahertz, down to basically the confusion limit. I'll show you what that is in a second. So just for those of you who don't do astronomy, this is the galactic center, Sag A star, where this black hole is. Sag B2, Sagittarius B2 is one of the clouds associated with the galactic center. And I looked at this northern position. So the scale here is very large. So here's what the spectrum looks like. Now we didn't have the privilege of some multiplexing where we could record this in one shot. We basically recorded the data in 1 gigahertz chunks. That's what our back end allowed us with the telescopes. And so there's all the spectral lines, about 15,000 across this broad range. And this is real. Sometimes you get some absorption signals. And if you zoom in on any 1 gigahertz section, it looks like this. Yeah, this is the problem you have to deal with, okay? If you're interested in complex molecules. So you can see a lot of organics. There's SO2, ethyl cyanide, formamide, and then mu is unidentified. And this is the noise level. So you're showing me some complicated spectra. Well, these are probably worse. This is just an astronomer's way of viewing intensity. Don't worry about it versus frequency. Okay. So this is almost completely analyzed, all 15,000 lines. Twain Hoffman's been doing this. And this is just for some organic chemistry aficionados. If you actually looked at the organic content of this cloud, the most abundant molecules are the alcohols, in particular methanol, but the ones with the greatest number of different species are the cyanides. So the cyanides are playing a role in gas-phase chemistry. And you do see simple sugar, like simple sugars, glycolaldehyde. You see some things with peptide bonds, amides, carboxylic acids. Like I said, the most abundant are alcohols. There's a lot of methanol out there. Okay, so here's how you can get so confused about an interstellar detection. You have to be so why this broadband coverage really helps us. So a few years back, there was this Stardust mission, and Stardust went to a comet surface. They claimed that there was ethylamine in this comet, but it turned out there was something wrong with their instrument. But at the time, they didn't know that, and so we said, oh, we're going to go look for this in the Sagittarius B2 North Cloud. We looked at the spectroscopy. It really hadn't been completely done, and so we went and measured millimeter and the microwave spectrum of ethylamine and figured it all out. It has some internal rotation or some inversion. And after all this work got done, there was like 72 very favorable transitions in this survey. And of course, we started looking at them. And oh, there was a shoulder that could be this transition 514, 413, and then there's a line here. And we know something about what the line width should be, so, and exactly where it should be in terms of its Doppler shift. So, you know, we could say that that's probably due to that, and there's another line there. But then if you continue to look at your various transitions that are favorable, now this one's not there at all, and it should be. And this one's not there at all, and it should be. And so by looking at all 72 favorable transitions, if you find 50% are missing, it's not there. Sorry, this is just line confusion. But if you aren't careful enough to do the spectroscopy and look at the appropriate number of lines, you can easily come to the wrong conclusion, and there have been numerous wrong conclusions because people didn't bother to look into the spectroscopy carefully. But not everything is a negative detection, but this is a new thing that we just recently found out in this cloud, a new interstellar molecule, which is methyl isocyanate. Now, this is a very strange species. Well, not strange, but it basically has the NCO group off axis in a very floppy, low energy bending mode, and the barrier to methyl internal rotation is virtually nothing. So this thing is spinning the methyl group and it's bending at the same time, so it's completely non-rigid rotor. And so the spectroscopy of this molecule hasn't really been completely investigated, at least up to now. Now I think a lot of people are doing it. And this molecule was recently found by the Rosetta mission on comet P67P. I don't want to even try to pronounce that. Churyumov-Gerasimenko. Everyone calls it comet P67. They actually landed a spacecraft, the Philae lander, actually landed on a comet, and it bounced on the comet head. It bounced a few times, kicked up dust, and in the mass spectrometer, they found methyl isocyanate. So of course, you read about this in Nature, and we're going to go check our big spectral survey. And so we go and you find there were lab measurements only up to 40 gigahertz done by Kaput and various other people. Bob Curl actually worked on this molecule way back when. This guy Kaput was the only one that could come up with a Hamiltonian to analyze the data, and he had a 3 megahertz RMS over a few hundred transitions in the 5 to 40 gigahertz range. And our survey range starts at 68 gigahertz, and so basically we had to go back in the lab and do some more measurements, and so we did them with the Fourier transform spectrometer. So here's just some of our spectra at 68 and 86 gigahertz. There's some nitrogen hyperfine in here, which sort of smears it out. But these new measurements combined with the previous work and the genius we had to get to analyze the data, the Illusion in Ukraine, we actually took our measurements and real measurements, and we did some predictions. But we did enough direct measurements and had good enough predictions such that we had very good transition frequencies for our survey, and we looked for the very distinct pattern of an A-type symmetric top. A dipole is the largest. And so we were able to actually find this molecule in the survey. And the survey data is the black, and our predictions with line shape and the relative intensity all predicted are overlaid in red. And every place we looked, we found a line, there were no holes, this molecules were detected, and it's some percent of the water. People that study comets compare everything to water, and comet P67, it's 1%, and it's at it's less than 1%. But you just have to do things properly and have a very consistent data set if you want to detect anything more complex in the diatomic test case. The other interesting point here, and I don't think I've made this clear enough, is that some molecules, you don't find other molecules. It can have the same combination of atoms. Interstellar chemistry is not combinatorial. Okay, so I'd like to finish this talk with just a little bit about our new antenna, our new radio telescope that we got, and where rotational spectroscopy can lead you down paths you never expected to go. This story all began a few years ago. The Atacama Large Millimeter Wave Array project, that one in Chile with the 50 telescopes, that's an imaging instrument. When the project began, they built 3 prototype 12-meter antennas at the very large array site. You can see one of the VLA antennas in New Mexico on the plains of St. Augustine. One was built by the US, the Vertex antenna, built by Vertex. One was built by the Europeans, most of it by European Industrial Engineering, EIE, and then there was a Japanese one built by Mitsubishi. When the testing was done, the Japanese took their antenna back, and these 2 antennas were sitting there on the site, and there was talk about moving them down to Chile, but then that was too expensive, and there were other reasons. And so, in the end, we got the European one, but it began with this letter in May of 2010, basically from the National Radio Observatory saying, on the behalf of the National Science Foundation, are you interested in this prototype North American Vertex antenna? And of course, if you are interested, let us know, and you can have it for free, okay, provided you move it. Now, they're worth about $14 million. So, I'm sitting there thinking, I'm running this old 12-meter, and, this would be great. So, any intelligent person would have jumped on this, and so we ended up writing this big proposal, which was our letter of intent. And we went to look at the 2 antennas, and that's out at me and Bob Floyd, one of my electrical engineers, out at the VLA site in June of 2010. And, everything changed for me at that point. And so, in the end, the Vertex antenna was given to the time lapse, okay? Don't ask me why, but this is what happened. And there was sort of a big blow up, and this article appeared in Nature, and so, in the end, we ended up getting the other one, which is the European one. We got it in exchange for some observing time for the European Southern Observatory. And so, basically, we got this letter saying, are you interested? And NSF gives the Vertex antenna to Taiwanese, and then there was a big protest, and then the NSF says, well, are you interested in the European one? We can help you. We said yes. We contacted the European Southern Observatory that owned it. Negotiations and property, all this sort of thing. And then finally they signed it over to us in March of 2013, so it was ours. We ripped out the old antenna and then moved the new antenna from New Mexico to the top of Kitt Peak. And we recommissioned it last year, and it's now completely working. And this was done pretty much by my small staff. Yes, question?
How much did it cost to move it?
$1 million. Okay, so this is not a little structure. It weighs 97 tons. And the European one was, you couldn't just unbolt it. I mean, first of all, there's all this electrical wiring between all the parts. And so this whole thing is carbon fiber. It was flown out to the VLA site in 2 pieces, glued together. This is carbon fiber. That's glued together. You don't want to cut carbon fiber, okay? So you're not going to take this apart. It's 12 meters in diameter. That's 40 feet. You're not going to take this apart, okay? And so we decided, and I wanted the least disassembly as possible, just to transport it in 2 parts: the reflector and the rest of it. Okay, and this was bolted to that, so that was fortunate because we could disassemble it that way. And so Mike knows all of this anyway. So anyway, this just shows you the scale, because this is us up at the man lift at the VLA site, and you can see how big this thing is. So transport 2 sections, the 75-ton base and what we call the receiver cabin. This is carbon fiber, this is steel, on a big specialty day truck. And then the reflector in bird bath mode on the highway, 40 feet in diameter, up Kitt Peak. The road's too narrow, so it had to go on a tilt plane. Okay, and I will show you a very short movie of the move, if you would like. It's about 5 minutes, but just to show you the difficulty. comes with music. This was actually made by the company Precision Heavy Haul. So the first thing we did was lift the dish out and set it aside, and then they transported this part first. And these were special lifting fixtures. Here comes the truck. These crane guys are pretty amazing. And that's out at the VLA site. And then this part went to Arizona first. This is November 2012. Here it is on its truck, leaving the VLA site, the base part. Cattle guard. Yeah, we had to do coming out of the VLA site into Socorro, New Mexico, through downtown Socorro. And then it went up to the mountain on a different truck. I didn't show that, but this is coming up Pit Peak, up to 6,300 feet. This is on an 8-axle gold hopper. They call it 8 individually steerable axles. That's what this guy is doing sitting here. We don't want to drop it. And then it was lifted into the dome the next day in a snowstorm. This was a very critical move. The crane went into overload. They couldn't put it down. Brought another crane in. And that's the dome where the old telescope was removed from. And then the dish came 2 weeks later. This had to be transported at night because it was the widest load ever transported in Mexico and Arizona. So this went through New Mexico like this. Christmas time. This is downtown Sapporo. You can see we had to take a lot of parts off, so the feed legs are gone, and there was some panels which are gone. One of the concerns were the overpasses. Then they had to be put on the tilt frame. Another critical lift. That weighed about 10, 12 tons. That was a little bit more fragile. This was all carbon fiber, and it had panels on it. The rhodium skin.
Why rhodium?
Sorry?
Why rhodium?
Rhodium, because it has the least reflectivity of any metal, and you could look at the sun without burning the self-reflector up. There it is, ready to go, and then it went up to the top of the mountain the next day. There it is coming up the mountain. That's the speed it went.